Hello, everyone. First of all, I'd like to thank the organizers of the conference for letting me record a talk for you all, and also thank you for your interest in watching my talk. All right, I'm Erik Zaborowski. I'm a grad student at Ohio State University, and I work with Professor Klaus Hohenscheid as well as Peter Taylor. And I'll be talking about measuring H naught without the sound horizon. And I hope that by the end of this talk, you'll be as excited as I am about this measurement, and especially its potential going forward in the era of powerful surveys like DESI. So this talk will be based on a recent paper of mine, which you can see here, and it's now accepted, as well as some work in prep that we plan to release very soon. And then I'll also talk about what prospects look like going forward. Okay, so first I will set the stage with some well-known physics. When you look at the clustering of galaxies, there are multiple features that can be used as standard rulers to measure cosmological parameters. A ubiquitous one is the sound horizon scale, which you can see here as the characteristic bump in the galaxy correlation function. And it has a co-moving size of about 100 over h megaparsecs. And this is the primary source of information for many of the well-known high precision measurements of the Hubble constant coming from things like CMB or BAO. And as you may have gathered from the title of this talk, we'll actually be focused on removing this information from our measurement. And when you do this, most of the remaining information then comes instead from the matter radiation equality scale. And the matter radiation equality scale is somewhat larger than the sound horizon scale with a co-moving wave number of about 0.015 h inverse megaparsecs. And that generally makes it a little harder to measure, both because of cosmic variance as well as large-scale systematics. But as you'll see later, DESI is really pushing this towards a precision measurement. So given that there are multiple cosmological standard rulers, in principle, this means that we can make multiple measurements of H naught. And this is interesting for a couple of reasons. First, because the sound horizon is what drives many of the early universe H naught measurements, like I mentioned before, this is usually the primary target of proposed solutions to the Hubble tension. And a popular example of this is early dark energy, which increases the early time H naught measurement by decreasing the absolute sound horizon scale, which brings it more in line with local measurements like from supernovae. And importantly, each standard ruler is probing physics at somewhat different times. So the sound horizon is probing physics around a redshift of 1100, while the equality scale is probing physics around a redshift of 3400. And because of these two things, we can ask a couple of questions. First, is H naught measured from the equality scale still in tension with local measurements like supernovae? But second, is H naught from K equality in tension with H naught from the sound horizon? And both of these questions probe modifications to early universe physics like early dark energy, because generically, these two scales are anticipated to be impacted differently. So with that in mind, let's move on to our measurement. So here is the list of the data sets that we used. First, we took DESI DR1, which has the positions and redshifts of about 5 million galaxies and 6 redshift bins. And we also included the AP effect measured in the Lyman-alpha forest, which gives additional information on the matter density, and also a BBN prior on the baryon density. And then on top of this, we layered on CMB lensing from Planck and ACT, as well as separately combining with each of the DES Year 5, Pantheon Plus, and Union 3 supernova data sets, which is similar to the main DESI papers. And if you haven't thought about this before, it may be counterintuitive, but only one of these data sets actually contains sound horizon information, and that is the DESI clustering. And in particular, Erik Baxter and Blake Sherwin pointed out that in CMB lensing, the projection along the line of sight washes out sharp features, including the BAO. So that makes it automatically free of sound horizon information. Okay, so given that the DESI galaxy clustering contains information from the sound horizon scale, we need a way to remove it from our measurement. And to do that, we used a technique that was developed in a 2022 paper by Garrett Farron, along with Oliver Philcox and Blake Sherwin. And the idea behind this technique is to first split the power spectrum into a smooth part and a wiggly part. And then you rescale only the wiggles by a new parameter that we called QBAO. So on the left, you can see the formula that corresponds to that transformation. And on the right, you can see the effect of varying QBAO, where values larger than one move the wiggles forward and smaller than one move them backwards. And this is a heuristic transformation, but it roughly has the same effect as changing the sound horizon scale. So by allowing this parameter QBAO to vary during inference, we're effectively marginalizing over the sound horizon information. And in Garrett Farron's paper, where they did a measurement with this technique using the VOS data, they did several tests and showed that indeed the sound horizon information is removed from their measurements using this technique. Okay, so moving on to results. I'm starting by showing our constraints before adding supernovae. So the blue contours here on the right show the constraints from the DESI clustering alone. And the orange contours are what we get after adding on CMB lensing, and then the green contours are what we get after adding on constraints from the Lyman-alpha AP effects. And then shown on the left here is our H0 constraint from only the DESI clustering, and we can compare that to a similar constraint from VOS DR12 by Oliver Philcox et al. And we see that the measurement that we achieve using only 1 year of DESI data is already more precise than the measurement from the full completed VOS survey, which is very exciting. And then finally, here's our tightest constraint independent of supernovae, which is in the mid 3% precision range. Okay, so now let's take a look at our full results. So these are the measurements using each of the 3 supernova data sets. You can see contours on the right and the 1 sigma constraints on the left. And if you average these, it comes out to a sub 3% constraint on H0 without the sound horizon, which is the most precise of its kind to date. And as I'll talk about later, there is still room to push this even further. Okay, so before moving on, let's talk about the implications for early universe physics. So in this chart here on the right, you can see a landscape of H0 measurements. At the very top are our k-equality-based measurements, both from the DESI clustering alone, as well as the full results with each of the 3 supernova data sets. Below that in pink are the DESI DR1 full shape results. In blue are the BAO results, and in orange are the measurements from the CMB. And then at the bottom of the chart are local measurements from supernovae. And so you can see the recent measurements from CCHP and SHOES, as well as a measurement from their combined subsamples using JWST. So looking at this plot, there are 2 things that I would take away. The first is that even without including information from the sound horizon scale, our measurements are still in up to 3 sigma tension with SHOES. The second is that our measurements are consistent with the other early time probes that do rely on the sound horizon scale. And this fact doesn't provide any evidence for new physics like early dark energy, at least at the precision of DESI DR1. And then I'll note that there are certainly models of EDE and so on that fit within these bounds. So it'll be very interesting to see what happens as we push the precision even further on this measurement. Okay, so in the last few slides, I want to talk about what we can look forward to in the future. For one, DESI is still collecting and releasing much more data. So conservatively, we can estimate that just because of the increase in survey area alone, even in the upcoming DR2, we'll have something like a 1 over root 2 improvement in the constraints, which is significant on its own. But beyond that, we're working on some updates that can significantly improve even the DR1 results. And I'll talk about these more in the following slides, but some things that we're working on right now are adding uncalibrated post-recon BAO, as well as getting a better handle on the nuisance parameters in the analysis. And we expect that these updates should place pretty strong constraints on new physics. Okay. Unfortunately, I can't show any of the early results from our work in prep, but I can talk about what we're working on. So one major update is that we're working on adding uncalibrated post-recon BAO data to our measurement. And conceptually, you can see what that means by looking at this figure on the right from the DESI DR1 BAO paper. So in the standard BAO analysis, if you don't use a prior on the baryon density, the absolute size of the sound horizon scale is unconstrained or called uncalibrated. But however, even knowing the relative sound horizon scale between different redshift bins gives a constraint on the matter density, which you can see from the intersection of the constraints from the different tracers at different angles. So I'll note here, you can see on the x-axis that H0 is still not constrained because it's perfectly degenerate with the unknown sound horizon scale. So while we are using a BBN prior in our analysis, because we freed that parameter QBAO, A similar effect occurs, which allows us to add the additional omega matter information from this effect without including sound horizon information. And of course, we'll properly account for the covariance between the full shape and BAO measurements, very similarly to how it's handled in the main DESI papers. And because we're including post-reconstruction BAO data, another benefit to this is that it brings in information beyond the two-point clustering, which is not present in our current full shape constraints. And I'm also excited about this update because our current results, the ones that I showed you before, are fairly dependent on the supernova data sets, and in particular, their omega matter constraints. And this addition will allow us to release a supernova independent measurement, which we plan to have out very soon. Okay. Finally, in the future, I also expect significant improvements from better constraining the EFT nuisance parameters. So just doing a very naive forecast, if we knew perfectly the values of all of the bias parameters and EFT counter terms, we would get something like 50% better constraints. And that's roughly evenly split between the biases and the counter terms. So any improvement we can make in constraining these parameters will lead to a large benefit in our results. And there are some known ways that we can nail these down better. And that includes, for example, cross correlations with CMB lensing or HOD-informed priors. And we have plans to investigate these in the near future. Okay, so that brings me to my conclusions. Again, we achieved a sub 3% constraint on the Hubble constant without using any sound horizon information, which I think is really exciting. And we still see up to a 3 sigma tensionless shoes. And also our consistency with sound horizon-based measurements for now doesn't provide any evidence for new physics in the early universe. But there's a lot of potential for this measurement in the near future, and it should lead to some interesting results. So stay tuned. Thank you.